Good day, everyone. The outline of Chapter 6, Exponential and Logarithmic Functions, are the following. 6.1. Exponential and Logarithmic Functions, a review. 6.2. Derivatives of exponential and logarithmic functions. The overview of the chapter introduces a basic review on exponential and logarithmic functions, its properties, and graphs. It also introduces the basic formulas on the derivatives of exponential and logarithmic functions and some applications. And lastly, it introduced proofs of the basic formulas on the derivatives of exponential and logarithmic functions. The objectives of the chapter contains the following. At the end of this chapter, the students are expected to: first, identify the exponential and logarithmic functions and its graph. Second, determine the basic derivatives formula of exponential and logarithmic functions. Third, find the derivatives of functions involving exponential and logarithmic functions. And fourth, solve some applications using the derivatives of exponential and logarithmic functions. So for today's first topic of Chapter 6, I will discuss to you the exponential and the logarithmic function, which will serve as a review to you for the upcoming next topic later. So first, let us all recall what is an exponential functions. Well, according to a trusted source I got in Google, an exponential function is a mathematical function in the form of the function of x is equals to a raised to the power of x, where x is a variable and a is a constant, which is called the base of the function, and it should be greater than 0. So meaning, a function is considered as an exponential when there is an exponent in a constant base. So, according to the book that we use in Calculus 1, a simplified text in differential calculus, the function of y or the function y is equals to a raised to n is called the exponential function. Since the base a is raised to an exponent n. I know that you are still familiar with the basic laws of exponent. As a review again, I will still discuss about this topic. So, shown in your screen is the different basic laws of exponents. First, any base or, as an example, base a raised to the exponent n is equals to the product of the base itself with respect to the exponent n. So, for example, 5 raised to 2 is equals to 5 times 5. So, 5 times 5 is equals to 25. Meaning, 5 raised to the power of 2 is equals to 25. Next, basic law of exponent is represented as a raised to m or raised to the power of m multiplied by a raised to the power of n is equals to the product of base raised to the sum of the exponents. For example, 2 raised to 3 multiplied by 2 raised to 4 is equals to 4 raised to 7. 4 since base times base or 2 times 2 is equals to 4. When multiplying a 2 base with an exponent, we will always add the exponent, then simplify. So 4 raised to 7 is equals to 16,384. Number 3, or the number 3 basic law of exponent, shows that a raised to the power of m divided by a to the power of n will always result to a raised to the power of m minus n. So when we divide an exponential expression, always remember that we are going to subtract its respective given power, or what we call the exponent. Next, open parenthesis a raised to the power of m close parenthesis raised to the power of n is equals to a raised to the power of m times n. In this basic law of exponent, it only means that we are going to multiply the given exponents since they are separated by a parenthesis, which means we are going to multiply. Next one. Any base which are combined with a parenthesis and is raised to a particular power of an exponent is equals to its respective base raised to a common exponent used. It is read as open parenthesis a, b, and c, close parenthesis raised to the power of n is equals to a raised to the power of n times b raised to the power of n times c raised to the power of n. So next, number 6. The same with number 5, which is only difference is the operation used. We are going to give the respective exponent to the given base, meaning, based on the given illustration in number 6, open parenthesis a over b, or a divided by b close parenthesis raised to the power of n is equals to a raised to the power of n over b raised to the power of n. So, in number 7, we must know first the fractional exponents for us to be familiar with the given law. So, a raised to the power of m over n is equals to the root of n, a raised to m. Number 8 states that a base raised to a negative exponent is always equal to the inverse of the given exponential expression. Meaning, if a is raised to negative m, it will result to 1 over a raised to m, or 1 over a raised to negative m is equals to a raised to the power of m. And lastly, any base which is raised to a zero exponent will always result to 1. So if a is raised to 0, its result is equals to 1. So those are the basic laws of exponents. Next, we are going to familiarize what is a natural exponent or natural exponential and its function. So, natural exponential function can be represented by the mathematical form of y is equals to e raised to x, or in a functional notation, the function of x is equals to e raised to the power of x, in which e is represented as any value of a constant or natural numbers, or simply the number e is also known as the Euler's number, which is a mathematical constant approximately equal to 2.71828. Shown in your screen are the properties of natural exponential. Just like in the basic laws of exponent, there are some laws which are applied to the different properties of the natural exponential. So number 1, e raised to the power of x multiplied by e raised to the power of y is equals to e raised to x plus y. So this is the same with the basic law of exponent like I've discussed earlier. So number 2, e raised to x divided by e raised to y is equals to e raised to the power of x minus y. Then number 3, open parenthesis e raised to the power of x close parenthesis raised to the power of y is equals to e raised to x y, or x times y. So e raised to x times y. So number 4 property states that the natural logarithm of e raised to the power of x is equals to x, or the exponent itself. Lastly, number 5 property states that e raised to 0 is equals to 1, since any constant that is raised to 0 is always equal to 1. So note that the natural exponential is the inverse function of the natural logarithm. I will further discuss to you what this note I've mentioned to you is all about. So now, I will discuss to you the logarithmic functions. So, logarithmic functions, note that logarithm is the inverse function of the exponential function. So this is what I mean when I told you earlier that the natural exponential is the inverse of natural logarithm. These two are related from one another. If we have an exponential function a raised to y, is equals to x, its logarithmic function would be the logarithm of base a of x is equals to y. So remember that logarithm, the result of a logarithm is the exponent. So I know that you are already familiar with this topic since we already learned about this during our first year subject trigonometry. So I will not further discuss this topic. Now we have forms of logarithm. The first one is the common logarithm and the second one is the natural logarithm. So what is a common logarithm? A common logarithm is the logarithm to the base 10 and is mathematically represented as the logarithm of base 10 of x is equals to the logarithm of x, while the natural logarithm is the logarithm to the base e, which is the natural exponential and is mathematically represented as the logarithm of base of x is equals to the natural logarithm x, or the natural are represented as ln x. There are different properties of logarithm. Number 1. Logarithm of base a of x and y is equals to logarithm of base a of x plus logarithm of base a of y. So this is the first property of logarithm. So the second one is the logarithm of base a of x over y is equals to the logarithm of base a of x minus the logarithm of base a of y. So these are the same with the basic law of exponent, but the difference is that this is a logarithm. So number 3. Logarithm of base a of x raised to y is equals to y multiplied by logarithm of base a of x. So number 4. Logarithm of base a of 1 is equals to 0. Since any constant which is raised to 0 is equals to 1. So number 5. Logarithm of base a of a is equals to 1. It is equals to 1 since any constant which is raised to 1 is equals to the constant itself, to the value of the constant itself. So number 6, logarithm of base a of a raised to x is equals to x. And lastly, number 7, a raised to the logarithm of base a of x is equals to x. So in this, note that in calculus, the most convenient and useful form of logarithm is the natural logarithm. So in the next slide, shown in your respective screen is the relationship between the graphs of y is equals to e raised to the power of x and y is equals to the natural logarithm of x, or ln x. So you can see that the natural exponential is the inverse of the natural logarithm, or vice versa, like that.